Usually when we think about power like real earth-moving power,
Hmm.
we picture massive diesel engines, right?
Right, absolutely.
We imagine these gears the size of dining tables, steel cables as thick as your arm, and, the deafening roar of combustion. We have this deep-seated expectation that to move something really heavy, the mechanism itself has to be rigid, metallic, and incredibly loud.
It is. It's a very mechanical, almost Victorian way of viewing the world, I think.
Yeah.
We like to see the levers.
Yeah.
We want to see the pulleys. It gives us a sense of understandable linear causality.
Yeah.
You push a rigid stick here, and the other end of the stick moves over there.
Right, but then you look at an excavator tearing its way through solid rock on a construction site.
Mhm.
Or actually think about the landing gear of a massive commercial jet deploying against hurricane force winds right before touchdown.
Oh, yeah, that's a great example.
The thing actually doing the heavy lifting in those extreme scenarios isn't a giant steel gear, it's a fluid. It's literally just oil rushing through a flexible rubber hose. And suddenly, that rigid mechanical worldview just feels a bit incomplete.
Well, it fundamentally is, because what you're describing is the absolute definition of fluid dynamics in action. The rules governing that immense power are entirely different from the rules of solid mechanics.
Right.
You are no longer dealing with fixed levers. You're dealing with the transmission of pressure through a medium that can, well, change its shape on the fly.
Which is exactly why we're here today. We've got a fascinating stack of research in front of us, pulling from engineering texts, university lab materials out of Boston University and the University of Maryland, and a handful of really cutting-edge physics papers.
It's quite the pile.
It is. And our mission for this deep dive is to map out the hidden rules of fluid power in motion. But we aren't just staying at the construction site. We are going to scale this all the way down to microscopic traps made of pure light.
Which is wild.
Seriously mind-bending. We're going to look at smart materials that survive the vacuum of space and figure out the weird mathematics of how continuous flow actually works. So are you ready for this?
I am. It's a journey that really challenges our basic intuitions about how things move and interact. Because as we change the scale of the environment, the physics that we take for granted just completely rewrite themselves.
Okay, so let's start right at the foundation, at the macro scale. Why do we even use fluids to move heavy things in the first place? To get a grip on this, we have to look back at the 1600s and a French scientist named Blaise Pascal. Let me throw a visual out there for you.
Okay, let's hear it.
If I walk up to you and push you in the chest with an open palm, you're going to feel it, right?
Sure.
It might push you back a step. But now, say I apply that exact same amount of driving force, but I only use the tip of my index finger.
Oh, that is going to leave a serious bruise.
Right.
The total force you're applying hasn't changed at all, but the pressure is vastly different because you've concentrated all of that energy onto a much smaller surface area.
Exactly. So Pascal looks at this relationship between force, pressure, and area, and he applies it to a closed system. Pascal's law states that if you have an enclosed, incompressible fluid, something like water or hydraulic oil, and you apply pressure to it, that pressure is transmitted equally and undiminished in all directions throughout the entire container.
And that word right there, incompressible, that is the absolute linchpin of this entire physical law.
Let's break that down.
Yeah, we have to think about what the molecules are actually doing. If you compress a gas, like, say, the air inside a pneumatic system, you are dealing with molecules that have a lot of empty space between them.
So the gas just squishes into a smaller volume?
Precisely. It absorbs the energy you put into it like a sponge.
So if I push on a piston full of air, I'm basically just making the air hotter and denser before the other side even starts to move.
Exactly. But a liquid, like hydraulic oil, has molecules that are already practically shoulder to shoulder. It essentially refuses to be compressed any further.
It just won't budge.
Right. Because it won't squish, the energy you introduce has nowhere to hide. It can't be absorbed as volume reduction. It has to be transmitted instantly throughout the entire system.
Okay, so translate that into a machine for us. What does this refusal to squish actually buy us from an engineering perspective?
It buys you massive force multiplication. Imagine you have a small cylinder with a piston that has an area of, let's say, 1 square inch. And you push down on that piston with 10 pounds of force.
Okay, tracking.
According to Pascal, you've just pressurized the fluid to 10 pounds per square inch. Because that fluid is incompressible, that 10 psi travels through a flexible tube to a second cylinder. Let's say the second cylinder is massive. It has a piston with an area of 100 square inches.
Wait, so the 10 pounds of pressure is pushing on every single one of those 100 square inches.
Yes, exactly. That 10 psi pushes on all 100 square inches independently. So your initial 10 pounds of force has just been multiplied into 1,000 pounds of lifting force on the other side.
That is just wild. I can push with 10 pounds and lift 1,000, but I mean, there has to be a catch. Physics doesn't just give you 1,000 pounds for free.
No, you're right. There is a catch, and it's the conservation of energy.
Yeah.
To lift that 1,000-pound weight by just 1 inch, you have to push your small 1 square inch piston down 100 inches.
Ah, okay.
You trade distance for force.
That makes sense. That tracks. But even with that trade-off, this gives hydraulic systems an unparalleled power density. Like, you can literally hold a 5 horsepower hydraulic motor in the palm of your hand.
Oh, easily.
If you tried to hold a 5 horsepower electric motor, you'd need both arms and a back brace. Plus, if you stall an electric motor by asking it to lift something too heavy, what happens? The wires overheat and melt.
Yeah, they fry. Whereas a hydraulic motor can maintain massive torque at 0 speed all day long, the fluid just waits there, holding the pressure.
Wow.
And it acts as its own internal lubricant, plus it's infinitely variable. You get this incredibly smooth, precise control over hundreds of tons of force just by, slightly opening or closing a valve.
Which is why we see it everywhere. It's the backbone of construction equipment, aerospace flight surfaces, marine steering systems on giant cargo ships.
Absolutely everywhere.
But this brings up a really crucial engineering dilemma that our sources highlight. If this fluid power works so beautifully, so powerfully for giant macro-scale machines, what happens when we try to shrink these systems down?
That's the million-dollar question.
Right. Like, if I want to build a microscopic medical robot or a tiny lab on a chip, why don't I just build actuators and hydraulic valves the size of a human hair?
Because the moment you scale down to that level,
Yeah.
the physics we rely on completely flips upside down. I mean, it's totally different. The rules that govern a giant excavator do not apply to a microscopic tube.
The sources mention that when engineers first started designing microfluidic systems, and we're talking about channels that are maybe 1 to 100 micrometers wide, dealing with nanoliters of fluid, they quickly hit a wall. And apparently it's a very thick, sticky wall.
They collided with something called the tyranny of the Reynolds number.
Okay, let's unpack this Reynolds number, because I think a lot of people have heard the term, but it's really hard to visualize. The sources use a great swimming analogy. So picture this. You dive into a standard Olympic-sized swimming pool. You take a strong stroke, you pull the water past you, and then you just glide.
Right, you coast.
Yeah, your mass and your speed carry you forward through the water for quite a while. That carry through is your inertia. But now imagine that same pool is filled with incredibly thick, freezing cold honey.
Oof. The experience would be entirely different.
Completely.
In the honey, you wouldn't glide at all. The very moment you stop actively pulling with your arms, you stop dead.
Like hitting a wall.
Exactly. The friction of the fluid dragging against your body completely overpowers whatever forward momentum you had built up.
And that dynamic, the battle between your forward momentum and the sticky friction of the fluid, is what the Reynolds number is actually measuring.
Precisely. In fluid dynamics, the Reynolds number is a dimensionless quantity. It's essentially a ratio that compares the inertial forces in a system to the viscous forces.
Okay.
The actual math looks at the fluid's density times its velocity times the characteristic length scale of the channel it's flowing through, all divided by the fluid's viscosity.
Let me make sure I'm visualizing this correctly. At the macro scale, our normal swimming pool or a giant hydraulic hose on a tractor, the length scale is large, the water or the oil has room to move, inertial forces completely dominate the equation.
Yes. In those macro environments, the Reynolds number is high, often in the thousands or even millions. The fluid splashes, it swirls, it forms chaotic eddies and whirlpools.
It acts like normal water.
Right. It has enough inertia to overcome its own internal friction.
But look what happens when we shrink the system down to the size of a cell. In a microchannel, the characteristic length scale drops to just a few micrometers. The fluid isn't rushing. The average velocity might only be 1 micrometer per second.
It's incredibly slow.
Yeah, so even if you're just using plain everyday water, the math becomes absolutely brutal.
Because the length and the velocity are so incredibly small, the top half of that Reynolds equation shrinks to almost nothing. The viscosity, the stickiness takes over completely. At this microscopic scale, the Reynolds number plummets to well below 1.
Wow. And the sources call this the regime of Stokes flow or creeping flow, right?
Yes, and it is a fundamentally different world. To give you a sense of the physics, all fluid motion is governed by a notoriously complex set of math called the Navier-Stokes equations.
Okay.
But when your Reynolds number drops below 1, A huge chunk of those equations, the nonlinear parts that calculate chaotic swirling inertia, they simply vanish. They become negligible.
So without the chaotic swirling math, what does the fluid actually do?
The governing equation simplifies into a completely linear balance between pressure and viscous friction. The fluid becomes entirely predictable.
And entirely laminar. This was one of those mind-bending facts in the research for me. In this creeping flow regime, chaotic turbulent mixing is literally impossible.
Oh, absolutely impossible.
If you put two different fluids into a microchannel, say, a stream of red dye and a stream of blue dye, they do not swirl together to make purple. They physically can't.
It's completely counterintuitive.
Yeah.
Like you pump them in, and they will just flow side by side in perfectly parallel, distinct streams down the entire length of the tube.
Like a candy cane.
Exactly like a candy cane.
Yeah.
The only way they ever mix is through natural molecular diffusion.
Which is what, exactly?
Just the slow, random bumping of molecules across the microscopic boundary where the two colors touch.
It's beautiful, really, but it introduces a massive engineering headache. Because if the fluid is acting like thick honey and it's bounded by microscopic walls, the friction has to be immense.
Oh, it is.
So if the fluid is that resistant, how hard is it to actually push it through a tiny tube? Let's say I have a microscopic pipe and I want to pump water through it.
Well, this brings us to a fundamental physical law called Poiseuille flow. It dictates the scaling laws of fluids and cylinders. It tells us that the volumetric flow rate, like how much actual liquid you can push through the tube, is proportional to the pressure you apply, which makes sense.
Right.
But crucially, it scales with the fourth power of the channel's radius.
The fourth power. Let's really break down what that means for an engineer trying to build one of these things.
Think about it this way. You design a microhydraulic system. You have a tiny tube. Then you decide, you know what, I need this to be even smaller to fit on my chip. So you have the radius of the tube. You make it twice as narrow.
My gut tells me that if the pipe is half as wide, maybe it's twice as hard to push the water through, or I don't know, maybe 4 times as hard because we're dealing with the cross-sectional area.
Yeah, that's how electrical resistance works. If you have the radius of a copper wire, the electrical resistance goes up by a factor of 4. But fluids are vastly more punishing. Because of the viscous drag against the walls of the tube, having the radius of a pipe increases the resistance to flow by a factor of 16.
Wait, really? 16 times harder, just by making it slightly smaller.
It's an exponential wall. If you shrink the tube by a factor of 10, it becomes 10,000 times harder to push the fluid through.
That's insane.
It is. And this is exactly why traditional mechanical macrohydraulics are completely useless at the microscale. You would need immense, structurally impossible pressures just to drive a single drop of fluid power through a microscopic capillary using a mechanical pump.
So the pump would just break.
Yeah, the tiny pipes would simply burst long before the fluid ever moved.
So we're stuck. We have this goal. We want to manipulate microscopic things. You want to grab living cells, bacteria, maybe single strands of DNA, and move them around to study them.
Right.
But we can't use tiny mechanical hydraulic arms to do it because the viscous drag is too intense. The mechanical fluid power approach is just a dead end. So if we can't push the fluid to move the object, what on earth do we do?
We throw out mechanical fluid power entirely.
Okay.
We stop trying to use a physical medium to push the object, and we start using light itself to grab it.
Here's where it gets really interesting. I have to say, reading through this section of the lag materials felt like science fiction. We are talking about optical tweezers. I want you, the listener, to really picture this. You're looking through a microscope at a pool of that metaphorical sticky honey.
Okay.
There's a single living cell suspended in it. And without using any tiny robotic claws, without ever physically touching the fluid yourself, you just grab the cell, move it around, and measure its properties.
It literally functions like a tractor beam.
Mm.
But it's not fiction.
Mm.
It is grounded in a very real piece of quantum mechanics, specifically the de Broglie relation.
Now hold on. High school physics taught me that light is made of photons, and photons are massless particles. If they have zero mass, how can they possibly push or grab anything? How do they have momentum?
It's a great question, and it stumps a lot of people. Classical physics says momentum is mass times velocity. No mass, no momentum.
Right.
But quantum mechanics tells us that light behaves as both a particle and a wave. The de Broglie relation shows that a photon's momentum isn't tied to mass at all. It's inversely proportional to its wavelength. So even though light has no physical mass, the wave itself carries momentum through space.
Okay, I can sort of wrap my head around that. So the light wave carries momentum, but how does that translate into physically grabbing a microscopic glass bead or a cell?
Well, it all comes down to conservation of momentum. When you shine a light on an object, that light doesn't just pass through it perfectly. The object acts like a lens. You reflect some light, and it refracts or bends
Yeah.
the light passing through it.
Oh, because the speed of light changes slightly when it enters a new medium, like going from water into glass.
Exactly. And any change in the direction of that light beam means a change in its momentum. Now, the universe demands that momentum must be conserved. If the object bends the photon to the left, the photon effectively pushes the object to the right.
Newton's third law.
Exactly. There has to be an equal and opposite physical reaction.
So if I have a microscopic bead and a laser beam hits it, the light scatters off it. That scattering must impart a physical push.
Yes. This is called the scattering force. It's essentially the pressure of the light just pushing the object forward in the exact same direction the laser is pointing.
But I mean, pushing something away from you isn't a pair of tweezers, that's just a tiny laser cannon. It's a leaf blower. How do we turn a leaf blower into a trap that holds an object completely still?
This is where the sheer brilliance of the optical engineering comes in. You don't use a flat, even wall of light. You use a highly focused laser beam, usually a high-power infrared laser, so it doesn't burn the biological samples.
Okay, good call on not burning the DNA.
Right. And you pass that laser through a very specific lens called a high numerical aperture microscope objective.
That sounds expensive. What does it actually do to the laser?
It takes that laser beam and focuses it down to a microscopic, incredibly sharp three-dimensional point. And here's the key. The laser beam isn't uniformly bright. It's like a flashlight beam, where the very center is blindingly bright, and as you move out toward the edges, it gets dimmer and fuzzier.
Like a bell curve.
Exactly. In physics, we call that a Gaussian intensity profile. That specific profile is the secret to the trap. When a tiny transparent object, like a polystyrene bead or a cell, sits in that focused beam, it's sitting in a gradient of light.
Gotcha.
There are vastly more photons hitting the center of the bead than the edges.
Let me try to visualize the forces at play here. If the bead is perfectly in the center of the beam, the light bends symmetrically around it. But what if the bead drifts slightly to the left into the dimmer part of the beam?
Okay, so if it drifts left, the right side of the bead is now sitting in the blindingly bright center of the beam.
Right.
So the bead starts refracting a massive amount of those intense central light rays over to the left.
And to conserve momentum, if it bends the bright light left,
The bead must feel an equal and opposite force pushing it back to the right.
it pushes it right back toward the brightest center of the beam. It's totally self-correcting.
It is an elegant physical feedback loop. We call this the gradient force. The gradient force acts exactly like an invisible optical spring. The further the bead tries to drift away from the focal spot, the stronger the light pushes it back.
Wow.
And if you focus the light sharply enough with that high numerical aperture lens, the backward pulling gradient force becomes so strong that it actually overpowers the forward pushing scattering force we talked about earlier.
So it's trapped.
The bead becomes locked in a three-dimensional cage of photons, trapped right at the focal point.
That is just deeply profound. You are using the object's own ability to bend light as the padlock to keep it in a cage made of photons.
It really is beautiful.
But the research papers go further. They don't just use these tweezers to hold things still for a quick photo. They use them to measure forces that are so small they almost defy comprehension.
Oh, absolutely. We are talking about forces in the piconewton range. To put that in perspective, a newton is roughly the force of gravity, pulling down on a small apple.
Okay.
A piconewton is 1/1,000,000th of that apple.
And what are they measuring with a trillionth of an apple's force?
Biology, the mechanical forces inside your own cells. Using optical tweezers, scientists can take a tiny glass bead and chemically glue it to a single molecular motor.
Like chitin. The sources mention chitin. This is a protein that literally has two tiny feet and walks along the structural microtubule fibers inside your cells to transport cargo, like packages of neurotransmitters. It's basically a biological robot.
It really is. So they glue the bead to the chitin, catch the bead in a laser trap, and then let the chitin try to walk away down the fiber.
Oh, I see where this is going.
As the motor protein steps forward, it pulls the bead slightly out of the center of the laser trap. And remember, the laser acts like a spring, pulling back.
So by measuring exactly how far the bead moves from the center of the laser, they can calculate the exact pulling force of the chitin.
Exactly. They can measure its exact step size, which is about 8 nanometers, by the way.
Hmm.
And to control these traps and move them around, engineers use devices called acousto-optic deflectors, or AODs.
Yeah, I saw that in the notes, but it honestly sounded like magic. Using sound waves to steer a laser beam. How does sound physically bend light?
It's a brilliant piece of solid-state physics. An AOD is a special type of crystal. When you blast high-frequency sound waves, radio frequency acoustic waves, into this crystal, the sound travels through it as a pressure wave.
Okay.
It creates alternating bands of compression and expansion in the crystal lattice.
Like ripples moving across the surface of a pond.
Exactly like physical ripples. These high and low density ripples change the refractive index of the crystal in a repeating pattern. The sound wave literally turns the crystal into a physical diffraction grating.
Oh, wow.
When the laser beam hits those acoustic ripples, it bends. By simply changing the pitch, the frequency of sound wave, you change the spacing of the ripples, which instantly changes the angle of the laser beam.
That is wild. There are no moving mirrors, no tiny motors to break down or vibrate the table. You are just playing a high-frequency song into a crystal to physically steer a biological tractor beam.
It's incredible. It gives scientists sub-nanometer, sub-millisecond control over the trap, completely free of mechanical wear and tear.
Okay, so optical tweezers are incredible. They are the ultimate micromanipulators. But let's be real about the setup for a second. You have massive infrared lasers, high-end lenses, a crystal vibrating with sound waves, all sitting on a giant vibration-isolated table in a clean, climate-controlled university lab.
It's highly controlled, yes.
Right. But what happens when we leave the lab? What if an engineer needs to generate immense physical pushing force at a small scale in an environment where lasers are useless, where electronics will fry and active power systems are totally dead?
Well, now you're pushing us out of the laboratory and into extreme environments. You're talking about places where survival dictates simplicity.
Exactly. Put yourself in the shoes of an aerospace engineer. You are designing a rover for Mars, or maybe a deep space satellite. You are operating in the freezing, irradiated, hard vacuum of outer space.
Not a friendly place for delicate electronics.
Definitely not.
Sure.
And suddenly there's a catastrophic power failure. The internal temperature of your spacecraft plummets. Your mechanical metal parts are now at extremely high risk of something called cold welding.
Cold welding is a terrifying phenomenon in space. On Earth, the oxygen in our atmosphere coats all metals in a microscopic layer of oxidation.
Oh, like a protective skin.
Exactly. But in a hard vacuum, that protective oxide layer is gone. If two clean pieces of metal touch, their atoms don't even know they are separate pieces. They just share electrons and physically fuse together into a single solid lump.
So your hinges seize up, your valves fuse shut, the spacecraft is completely paralyzed. So my question is, how do you trigger an emergency mechanical safety switch, say, to open a thermal vent or deploy a backup solar panel when your batteries are dead, the computer's offline, and you have absolutely zero electricity?
You can't rely on electronics. You have to rely on thermodynamics. You use an autonomous actuator, specifically a phase change material, or PCM.
Phase change materials. When I read the sources on this, it sounded highly complex, but we're basically just talking about highly engineered wax, right?
At its core, yes. Certain paraffin waxes are excellent phase change materials. The principle here is elemental. When a PCM transitions from a solid state to a liquid state, when it hits its melting point, it undergoes a massive, violent change in volume.
Because the heat adds energy to the molecules. They break out of their rigid, tight crystal lattice, start vibrating intensely, and they just need more physical space to move around as a liquid.
Exactly. The expansion is substantial, sometimes a 10 to 15% increase in volume. Now imagine you design a rigid, heavy-duty metal cylinder. You fill it with this paraffin wax, and you cap one end with a tightly fitted, movable metal piston.
Okay, I see. When the environment gets hot enough to melt the wax, that 15% volume expansion has to go somewhere. The cylinder is rigid, so it can't bulge out the sides.
Right.
It has to push the piston.
And it pushes it with tremendous force. The thermodynamic expansion of melting wax doesn't care about the friction of the piston. It generates immense mechanical pressure.
The sources compare PCMs to other smart materials engineers, use things like shape memory alloys or piezoelectrics or bimetallic strips that bend when heated. But out of all of them, PCMs have the highest energy density. They can produce massive torque and displacement from a tiny little cylinder.
Which is precisely why they are the holy grail for space applications. They are entirely autonomous. They respond directly to the ambient temperature of their environment. On the U.S. Mars rover missions, PCM actuators were deployed as the ultimate fail-safe backup mechanism to regulate the temperature of the critical battery base.
So no sensors, no thermostat wiring.
None.
If the battery base starts overheating because of the Martian sun or heavy load, the ambient heat physically melts the wax cylinder sitting next to it. The wax expands, pushes the piston, and physically forces open a louvered thermal vent to let the heat escape.
And as the bay cools down, the wax solidifies, shrinks, and a return spring closes the vent. It's a mechanical system with zero computer logic, zero wires, and zero reliance on the main power bus.
That's brilliant.
The Japanese Sprint A spacecraft used a very similar PCM actuator to operate a critical vacuum gate.
But the sources also pointed out a really clever terrestrial application for this right here on Earth. Solar tracking arrays.
Oh, yes.
If you have a massive field of solar panels, you want them to tilt throughout the day to track the sun across the sky. That maximizes your energy capture. But usually you have to use electric motors to move those heavy panels, which means you're literally wasting some of the electricity you're trying to harvest just to run the motors.
It's an efficiency loss. So some engineers thought, why use electricity at all? Why not use the sun's own thermal energy to move the panel?
It's so clever. Let's walk through how this works for everyone. You attach a pair of these PCM wax cylinders to the edges of the solar array, connected to a pushrod mechanism. In the morning, the sun rises and hits the cylinder on the east side. The wax heats up, melts, and expands. The piston extends and physically pushes the heavy solar panel, tilting it toward the sun.
But here is the genius design element. As the panel tilts to face the sun perfectly, the frame of the panel itself is designed to eventually cast a shadow directly over the PCM cylinder that just did the pushing.
Right. The cylinder does its job, tilts the panel, and accidentally puts itself in the shade. Because it's in the shade, the wax cools down, solidifies, and contracts.
The panel stops moving. It locks into position facing the sun.
And then an hour later, the sun creeps further across the sky. It moves past the shadow, hits the wax cylinder again, heats it up, melts the wax, and nudges the panel a few more degrees until it falls back into the shade.
It is a continuous, self-correcting, completely passive mechanical feedback loop. It requires absolutely zero electricity. It just chases the heat of the sun all day long.
It's elegant, but it can't be perfect. If I'm an engineer looking at a cylinder of melting wax, pushing a heavy solar panel, or protecting a Mars rover, I have to be sweating about the structural integrity.
You've hit on the primary engineering limitation. The expansion of that liquid wax generates massive internal pressure. And when you have a highly pressurized hot liquid,
You have a recipe for a catastrophic leak, especially in space.
precisely, in the hard vacuum of space, if your rubber or metal seals fail even slightly, that hot liquid wax instantly boils off and vaporizes into the void. Your cylinder empties, your actuator dies, the vents stay shut, and your Mars rover's battery cooks itself to death.
Not ideal.
No. The core challenge with PCMs isn't generating the physical force. It's designing dynamic seals and containment vessels that can survive thousands of extreme thermal expansion cycles without weeping a single drop of fluid.
So phase change materials are fantastic for immense autonomous force, but they have a glaring weakness, speed.
There for you.
They are entirely dependent on ambient thermodynamics. You have to sit around and wait for the sun to heat up the wax and then wait for the shade to cool it down. It is inherently slow. What if an engineer wants the best of both worlds? What if we need a fluid that can change its physical phase from liquid to solid instantly, on command, without waiting for the temperature to change?
Then we leave thermodynamics behind, and we enter the realm of electromagnetism. We're talking about magnetorheological, or MR, fluids. This is where material science begins to look truly futuristic.
Okay, let's break down the chemistry recipe for an MR fluid. If I have a bucket of this stuff, what exactly am I looking at?
It starts with a base layer of a non-magnetic carrier fluid. Usually this is a synthetic oil, like silicone oil. Then you suspend a massive amount of microscopic magnetic particles within that oil.
The sources mention carbonyl iron as the go-to particle.
Yes, carbonyl iron is incredibly pure and has a very high magnetic saturation, meaning it responds powerfully to magnetic fields. These iron particles are tiny, just a few microns wide, but they make up a huge portion of the fluid, sometimes up to 50% of the total volume.
Wait, I have to stop you there. If I go into my garage, take a bucket of motor oil, and dump a massive scoop of iron dust into it, it's not going to stay mixed.
No, definitely not.
It's just going to sink to the bottom like sand in a glass of water. It's going to turn into a sludgy rock at the bottom of the bucket.
You're describing sedimentation, and you're exactly right. That was the primary failure point of early MR fluids. The iron is heavy, it wants to sink. This is why modern MR chemistry is highly specialized. The iron particles are actually coated with additives, often microscopic layers of silica, to prevent them from physically touching and clumping together.
So the silica acts like a bumper car shield.
Exactly. And then they add chemical surfactants to the oil. These can be as simple as specialized greases or oleic acid. The surfactant molecules attach to the iron particles and create a repulsive force between them, keeping them suspended in the oil and slowing down the sedimentation process.
That's smart.
It also coats the iron to prevent it from oxidizing, because rusty iron particles lose their magnetic properties.
Okay, so we have this perfectly stabilized suspension. Under normal conditions with no magnets around, what does it feel like?
It just looks and flows like a dark, somewhat thick, heavy motor oil. The iron particles are randomly distributed, just bumping around the fluid.
But the moment you bring a magnetic field near it,
The physical state of the material completely transformed,
boom.
instantly. The microscopic iron particles are instantly magnetized. They act like millions of tiny bar magnets. The positive pole of one particle violently snaps to the negative pole of the next one. They align themselves perfectly along the invisible lines of magnetic flux, forming robust, structured chains that stretch across the entire body of the fluid.
So the liquid effectively becomes a solid.
In physics terms, we call it a semi-solid state, or a viscoplastic state.
Mm-hmm.
The fluid develops a massive yield stress. It can withstand up to 100 kilopascals of pressure.
Wow.
It takes real significant physical force to break those microscopic iron chains and force the material to flow again.
And the most incredible part is the speed. The phase transition from free-flowing liquid oil to solid barricade happens in a matter of milliseconds. Turn the electromagnet on, it's solid. Turn it off, the chains break, and it's liquid oil again.
It's like flipping a light switch on the state of matter.
So this is amazing in a test tube. But how do engineers actually build a machine out of this bizarre property?
Let's look at the incredible research prototype built at the University of Maryland. They designed what they called an MR piezohydraulic actuator. It's an absolute masterpiece of integrating different smart materials into a single system.
Okay, let's look at a traditional hydraulic system first. Usually you have a mechanical pump pushing fluid, and then you have heavy mechanical valves that physically slide open and closed to direct where the fluid goes. But mechanical valves have friction. The metal parts wear out over time, they get stuck, or they leak.
So the Maryland engineering team decided to eliminate the mechanical valves entirely. They built a closed hydraulic circuit shaped like a wheatstone bridge. Imagine a diamond shape with 4 distinct pathways. In each pathway, they placed an MR valve.
Let's clarify what an MR valve actually is, because when I hear valve, I picture a door swinging shut. But an MR valve has no moving parts, right?
Right. It's just a hollow metal tube that the MR fluid flows through, with an electromagnetic wire coil wrapped tightly around the outside of the tube.
Exactly. The fluid flows through an annular gap inside the tube. There is no door to swing shut.
And to generate the fluid pressure, they didn't use a standard spinning motor pump. They used a piezo pump.
Right, piezoelectric materials. These are crystals or ceramics that physically change their shape. They expand or contract when you run an electrical current through them.
So they stacked a bunch of these piezo crystals, attached them to a steel piston and a flexible metal diaphragm, and ran alternating electrical current into the stack. Every time the current pulses, the crystals expand, driving the piston forward and pushing a pulse of MR fluid into the diamond circuit.
And this pump is fast. The lab notes say they were operating it at up to 600 hertz. That means the piston is vibrating and pumping fluid 600 times every single second. It's generating high-frequency, aggressive pulses of flow.
It is incredibly violent. Now imagine that pulse of fluid hitting the top of the diamond circuit. It has to choose a path. Go left down path A or go right down path B.
If neither of the MR valves in those paths is turned on, the fluid just splits evenly and flows down both sides.
But if the computer applies a very small electrical current, maybe just 2.0 amps, to the wire coil wrapped around path A,
The magnetic field activates. The MR fluid passing through that specific tube instantly forms those robust iron chains. In milliseconds, the fluid solidifies and builds a physical wall, blocking path A entirely.
Exactly. So all the hydraulic pressure from that 600 hertz piezo pump is instantly, violently redirected down path B. And at the bottom of the circuit, that fluid hits a hydraulic cylinder and pushes it to do actual physical work.
The performance stats on this tiny prototype blew my mind. Running the piezo pump at an optimized 250 hertz and applying just 2 amps of power to the MR coils, this system, which basically has 0 traditional sliding valves, lifted almost 3 kilograms of solid deadweight at a speed of 5.6 millimeters per second.
And because it uses MR fluid, it allows for incredibly precise proportional control. You aren't limited to just turning the valve fully on or fully off like a light switch.
How's
By varying the electrical current to the coil, you vary the strength of the magnetic field. A weaker magnetic field creates weaker iron chains. So instead of a solid wall, you create a particle blockage. You can dial in the exact yield stress of the fluid in real time, creating a perfectly controllable hydraulic brake or damper.
That's why they use MR fluid in the magnetic ride suspensions of high-end sports cars, right? The car's computer reads the road bumps and instantly stiffens or softens the shock absorbers by magnetizing the fluid inside them.
Exactly. But while the application is beautiful, the sources make it very clear that the mathematics required to model this flow for engineering purposes is painfully difficult, because once you magnetize it, this fluid is no longer a normal Newtonian liquid.
Yeah, it's highly non-Newtonian. You can't just use standard water pipe equations.
No. To predict how much weight the actuator can lift, the Maryland engineers had to delve into complex rheological models to describe how the fluid yields under pressure.
The papers debate two different mathematical approaches, the Bingham plastic model versus the Baviscus model. Break this down for us. What's the difference?
Let's use an analogy. Imagine a bouncer standing at the door of a crowded nightclub. The Bingham plastic model is the idealized, mathematically perfect version of that bouncer. It assumes that once the magnetic field is turned on, the fluid acts perfectly solid.
Okay.
The bouncer blocks the door with infinite strength and absolutely no one gets through until the pressure from the crowd exactly exceeds his strength, at which point the door flies wide open.
So it assumes the magnetic plug is a perfect, impenetrable concrete wall right up until it shatters.
Right. It assumes zero flow below the yield stress.
Yeah.
But physical reality is always messier than idealized math. In a real MR valve, even when it is strongly magnetized, the intense high-frequency pressure pulses from the piezo pump cause tiny amounts of the fluid to slowly creep or leak through the iron chains.
So the bouncer is strong, but a few people are still managing to squeeze past him through the cracks in the door.
Exactly. We call this pre-yield leakage. The solid plug isn't perfectly solid, it's slowly deforming. This is where the Baviscus model becomes essential. It accounts for this messy reality.
How does the math actually capture that leakage without getting bogged down in impossible physics equations?
The researchers handle it by defining the flow using two specific ratios. First, they look at the physical size of the blockage. Inside the cylindrical valve tube, the magnetic field is strongest near the metal walls. So the plug, the solid, unyielding core of magnetized iron chains, forms in the center. The engineers calculate the ratio of that solid plug's diameter compared to the total diameter of the valve.
Makes sense.
If that ratio is 1, the valve is 100% block solid. If it's 0, there's no magnet and it's just flowing Newtonian oil.
Okay, so that measures the size of the bouncer. What's the second ratio?
Second ratio measures the changing stickiness of the fluid. They take the viscosity of the fluid after the iron chains shatter and it flows freely and compare it to the apparent creeping viscosity before it yields, while it's still mostly solid but leaking slightly.
So by factoring in the size of the solid plug and the speed of the leakage, they get a much more accurate picture of the real-world friction.
And it proved to be the missing link. By plugging those two ratios into the Baviscus mathematical model, the Maryland researchers found that their computer simulations finally matched the real-world lifting tests perfectly. The pre-yield leakage, the people squeezing past the bouncer, was the exact reason the system wasn't 100% efficient.
It's a testament to why deep theoretical mathematics is absolutely necessary to tame these exotic smart materials. You can't just build it. You have to be able to mathematically predict its flaws to make it a usable industrial tool.
Exactly.
Now, speaking of the math of continuous flow, I want to bridge this into a totally different area of physics that the sources brought up. When we look at these MR valves pulsing fluid 600 times a second, creating this complex shifting resistance, traditional math struggles to measure the total amount of fluid displaced because it's not a steady, continuous stream. The state of the fluid is constantly changing over time.
It's very dynamic.
Right, and this brings us to a glaring hole in how we intuitively calculate movement.
It challenges the very bedrock of kinematics, really.
Let's take everyone back to high school physics for a second.
Yeah.
We all learned the holy trinity of kinematics: position, velocity, and acceleration.
Right. You start with your position or displacement. If you measure how your position changes over time, if you take the mathematical derivative of position, you get your velocity, how
Okay.
fast you are moving.
And if you go one step further and take the derivative of velocity, measuring how your speed is changing over time, you get acceleration.
Position derivative equals velocity, derivative equals acceleration. It is an elegant cascading system. It is how we calculate the trajectory of a baseball or the speed of a car.
But the sources pose a question that seems so obvious in hindsight, yet totally mind-bending. What if we go the other way? We know the derivative of position is velocity, but what happens if we take the integral of position? What does the area under the curve of displacement over time actually represent?
The result of integrating position over time is a formal physical concept called absentment.
Absement, let's be honest, it sounds like a totally made-up word.
It really does. It is a portmanteau of absence and displacement. It is a relatively new formal concept in physics, specifically in a field called integral kinematics. And while it sounds esoteric, it is profoundly important when dealing with continuous flow-based systems, like hydraulic valves.
To explain why absement matters, let's use the incredible musical analogy from the research papers. Think about a standard, modern, digital piano keyboard.
A digital piano is a strictly velocity-sensitive instrument. Underneath every single plastic key is a digital sensor. When you strike the key, the sensor doesn't just register that the key moved from point A to point B. It calculates the derivative. It measures how fast the key moved.
Because if you strike it quickly, the computer knows you want a loud, aggressive piano note. If you press it slowly, it plays a soft, gentle note. It's reading your velocity.
Exactly. It operates on the derivative of your finger's position. But now compare that to an instrument called a hydraulophone.
A hydraulophone. This is an absolutely fascinating piece of engineering. It's essentially an underwater pipe organ. Instead of a row of piano keys, there is a row of water jets constantly shooting streams of water. To play a note, you press your finger down over one of the water jets. By blocking the escape path, you force the pressurized water down into an internal sounding mechanism to create a musical pitch.
And here is the fundamental physical difference between the two instruments. The hydraulophone is not velocity sensitive. It does not care how fast you jam your finger onto the water jet.
Right.
The physics of the fluid don't respond to the derivative of your movement. The hydraulophone is absent sensitive.
Let's really break that down. Why is it measuring absement?
Because the total volume of water that is forced into the sounding mechanism, which dictates the overall volume, duration, and expressive swell of the musical note, is not just a function of how far down you push your finger to restrict the jet. It is a function of how far down you push it, multiplied by how long you keep it there.
That's the
Yes, it is the time integral of your finger's displacement. The fluid system essentially possesses a physical memory of the openness of the valve over time.
Let me make sure I'm wrapping my head around this. If I cover the water jet halfway, restricting 50% of the flow, and I hold my finger there for 2 seconds, a certain volume of water hits the sounding mechanism. But I could achieve that exact same total volume of water by pushing my finger down completely, blocking 100% of the jet, but only holding it there for 1 second.
Precisely. The final state of the system, the total flow, is identical in both scenarios. The hydraulophone mathematically integrates your physical effort over time. It responds to absement.
That completely changes how you interact with the machine. A piano responds to a moment in time. A hydraulophone responds to an accumulation of time. And the math of integral kinematics doesn't stop there, right?
No, it goes infinitely deep, just like derivatives. If you take the time integral of absement, you get a variable called abscity. If you take the integral of abscity, you get abceleration.
Okay, abceleration sounds like a fake word an engineer made up to win a bet. But seriously, how does this apply outside of weird underwater musical instruments? Is this just mathematical navel-gazing for theoretical physicists?
Far from it. It has profound practical implications for understanding complex systems, particularly human biomechanics and how our bodies consume energy.
Oh, really?
Yeah, the sources detail a fascinating scientific study on something called quasi-isometric muscle loading.
Break that down. What does quasi-isometric loading look like in the real world?
It basically means attempting to hold a steady, static posture under a physical load. Imagine standing on a balance board or a wobble board at the gym, trying to keep it perfectly parallel level, or even just trying to hold a heavy camera perfectly still to take a photograph.
Okay, so to an outside observer, or to a standard camera, you look completely stationary. Your position isn't changing.
But biologically, internally, your muscles are firing constantly. You are burning massive amounts of metabolic energy to maintain that stationary position against the force of gravity.
And the researchers discovered that if you try to calculate the calories burned, the metabolic cost of holding that pose using classical kinematics, the math completely fails.
If you attach a sensor to the wobble board and measure its velocity or acceleration, you are only capturing the high-frequency micro-oscillations. You're capturing the tremors, the rapid tiny twitching of your muscle fibers, constantly overcorrecting to keep you balanced.
But the tremors aren't the whole picture of the work you're doing.
No, because as your muscles fatigue, your posture is also slowly, systematically drifting away from the perfect center point. It's a microscopic sag over time. Velocity and acceleration don't capture that slow, steady, accumulating drift very well at all.
So because classical derivatives failed to predict the energy burn, the researchers applied the integral. They used absolute.
They did. They modeled the total metabolic energy cost as a sum of different mathematical variables. And they proved mathematically that the deviation absolute, the integral of your distance from the perfect center of balance over time, is the unique leading first-order variable that accurately captures the energy cost of that systematic physical drift.
So by using absolute, they could mathematically separate the metabolic energy you burn from just slowly sagging off-center, from the energy you burn rapidly twitching and tremoring.
Exactly. The tremors are captured by a separate quadratic term. By bringing absolute into the equation, they could perfectly predict the metabolic cost of holding a pose using very simple kinematic measurements.
It reveals something deeply profound about how humans operate. The human body and how it expends energy to maintain a posture against gravity is fundamentally an absolute-driven system. Our muscles act like the fluid in the hydraulophone. They integrate effort over time.
It proves that our biological reality is tied to the memory of displacement, not just the speed of it.
Okay, let's take a collective breath and recap the incredible journey we've just been on. Because we have covered a massive spectrum of physical reality today.
We really have traveled from the macro to the micro and back again.
We started at the human scale, looking at the sheer pushing power of Pascal's law. We explored how the molecular incompressibility of oil allows us to build force-multiplying giants like excavators. But then we shrunk our perspective down to the microscale and immediately hit the viscous wall of the Reynolds number.
We entered the regime of Stokes flow, where fluid acts like freezing honey, inertia vanishes, and turbulent mixing becomes physically impossible. We faced the harsh reality of Poiseuille's fourth power scaling law, which makes pushing fluids through tiny pipes thousands of times harder.
Which forced us to abandon mechanical pumps entirely. We had to learn how to bend the momentum of photons, using the Gaussian profile of a laser to create optical tweezers, trapping single DNA strands in a cage of light steered by sound waves.
Then we zoomed out to the freezing vacuum of space to discover how the massive volume expansion of phase-changing materials melting wax can autonomously steer solar panels and save Mars rovers without a single drop of electricity.
We came back to Earth to play with chemistry, suspending silica-coated iron in oil to create magnetorheological fluid, freezing it in milliseconds to build solid-state hydraulic valves vibrating 600 times a second.
And finally, we learned a completely new mathematical concept, absolute, the time integral of displacement, discovering that continuous systems like fluid flows in human muscles possess a mathematical memory of their position over time.
It is a completely different, almost alien way of looking at motion and power. Which brings us to our final thought for the day, when we step back and look at this entire deep dive.
There is a striking philosophical contrast between the physics we've explored and the world we currently live in. Our modern technological world is almost entirely digital. Our computers, our smartphones, our software interfaces, they are all built on discrete binary states. A transistor is either on or it is off. It is a 1 or it is a 0. And digital culture is fundamentally obsessed with velocity. How fast can a processor execute a command? How quickly can a touchscreen respond to a finger tap?
Digital logic is the ultimate derivative-based system. It values instantaneous speed above all else.
Precisely. But the natural physical world doesn't work like that. The flow of a river, the thermodynamic melting of wax, the yielding of magnetic smart fluids, the slow, fatiguing burn of human metabolic energy, the natural world operates on the continuous memory-holding logic of absolute. The universe integrates our actions over time.
So here is something for you to mull over as you go about the rest of your day. Put yourself in the shoes of an inventor. If the natural world is intrinsically absolute-driven, accumulating history over time, and our digital tools are strictly velocity-driven, there is a massive fundamental disconnect. Huge disconnect. What would happen if we redesigned our digital interfaces, our operating systems, and our tools to respond to the integral of our actions rather than just the speed of them? If a computer remembered the weight of your continuous effort, What entirely new, fluid ways of interacting with the physical and digital world might we invent?
That's a great question.
It really makes you look at a simple puddle of water, or even just the feeling of holding your arm out straight in a completely different light. The rules governing the universe are hidden, but they are always flowing, always accumulating. Thanks for taking the plunge with us today.